Welcome everyone to this 8th ALASCA Tech-Talk. I hope that most of you are, have made it past the post-vacation syndrome. Maybe some of you still have some holidays in the future, but yeah, I'm happy to see all of you here. In case anyone is joining new today for the first time, my name is Maria Vaquero. I am in the business development and marketing team of Cloud and Heat Technologies. Cloud and Heat Technologies is one of the members of the ALASCA Association. And so I usually moderate these tech talks. You have all noticed that the session is being recorded. So just again, for your information, keep that in mind. And so we have a very short agenda for today, as usual. We will start in 1 or 2 minutes with today's Tech Talk and discussion. I will briefly introduce the topic and the speaker, and then I will give over the microphone. And then we have a short session at the end with some information about news, events, changes to the Tech Talks. And there's also an opportunity for all of you to share with us if you have any events or news that you think would be interesting for the community. So today we have a presentation on confidential computing and how it can be used to protect data, applications, and code. And we have Christof with us today, who is going to be the speaker of the talk. I will briefly introduce him before handing over the microphone. So he has a PhD from the University of California and is professor at the Technical University of Dresden. And he has co-founded several companies, Cloud and Heat being one of them. And then also Celestial Systems, which is focused on functional safety, and Scontain, which is focused on confidential computing, which is the topic of today's talk. So with this, I will stop my sharing, and whenever you're ready, you can start, Christof.
Let me try to share. One sec. I hope you see my presentation.
Yes, we can see it.
Thank you for the introduction. How many minutes do you give me, and how should I allow the question during the talk, or do you prefer at the end?
Well, usually we have the presentation and then the questions at the end. And so we have in total an hour. It would be good if you could stick to maybe 20-25 minutes, and then we have enough time for discussion, because sometimes we have a lot of questions.
Okay, good. Sounds good. Thank you. Okay, so my presentation is about confidential computing. So the goal of confidential computing is that I protect my data that I process in my application or my services. Sorry, there was some background noise. So to protect my data, my code, also when I have Python code, for example, I want to make sure that my Python code is not visible to any adversaries. And also I have secrets, so like encryption keys that I want to protect, such that say admins cannot use my encryption keys to decrypt my files. And so I have some introduction slides that show you a little bit the motivation, also my standpoint, who I want to protect from, so who are the threats and who are the roles that I want to support. And my view is most of the time that I want to help the application owner, so the entity that defines a service or an application. This application owner might actually run an application, operate an application, and that application consists of data, code, and secrets, as I mentioned. And this application provides services to clients. So typically, this application runs somewhere, and the clients connect via their phones, via their browsers to that application. And the main focus is to protect the intellectual property of the owner, not necessarily of the clients. So if the client data is specially protected, might be an additional application requirement, but here our main focus on confidential computing is to protect the application itself. And in some cases, like in the electronic health domain, I need also to protect the data of individual clients like patients from each other. So if I'm a client and I have some data that is managed by the application, I should not be able to kind of use certain requests to get to the data of some other patient. So if I'm two, I'm not allowed to access the data of one, or patient three, even if I find some bug in my application, or not my application, the application's owner application. And so typically we have strong requirements in the electronic health domain. So if you see my cursor, so we have an owner, and even the owner might not be permitted to see all the application data. Despite owning the application, despite operating it, this owner might need to make sure that it's, or he or she cannot access the application data. We might have infrastructure staff that accesses all the infrastructure, takes care of, has root and admin access, but they must not be able to access the application and its data. There might be special service provider staff member that might need access to a subset of the data. Like if there's some call, some hotline that is called, maybe that a service provider has limited access to some of the data. And so what we sometimes do in this domain is that we, in particular in the electronic health domain, is that we might encrypt the different data with different keys. So client one or patient one might have encrypted data, patient two has encrypted data, and also patient three, and then maybe to part of that data, some staff member gets a key to access part of the data. So that means we have typically many keys in the system, and these keys are needed to access certain data. And we want to make sure that the owner and the staff members do not get access to the data or the code if we have Python code. And so the approach is to cryptographically protect our data, and we extend that also to cryptographically protect the code and secrets. So everything is encrypted, and only if I'm authorized, I can get access to the keys, and then I can decrypt the data and also the code to do all the things that I'm permitted to do. But if I'm not permitted, then I should not get access to any keys. So what is the problem here? So there is first a business problem, and second, there is a technical problem. So I first introduce a little bit of business problem, and then I go through to the technical problem. So the business problem is that if I'm an application owner, typically I have problems to find trusted staff that runs my infrastructure. So it's typically I might have people to build my application, but I don't have all the staff and the money to run my own application data center, or for each application data center. And so therefore I have problems, or how can I run my infrastructure? I might even have problems to run my own applications, or there is lots of detailed technical knowledge needed to configure my application, to modify standard applications. So I need to have lots of very expert skills to deploy an application today, because I have so many microservices that I need to adjust to make sure that they work together, and that needs really expert skills. And sometimes I might not have that, or in my team as an application owner, I might provide some services or might implement some services, but I might not have the full expertise in my members of staff. So therefore, I might need some external application service staff member that we are outsourced to. And so that means outsourcing is one way to deal with that business problem. So I need to get certain jobs done. I outsource that to external staff, so infrastructure staff, application service staff. And by doing so, I might lose control over my intellectual property, over my code that I have, over my data. Even my keys might not be in my control if I'm the application owner. And so therefore, I would like to solve that as application owner. So I need to have a solution to be able to outsource and still protect my intellectual property. So what are the technical challenges in this context? So first, if I have certain keys, like here I said before, I might partition my application data with cryptographically by encrypting for each client data with an individual key. If the keys are now in main memory, I, as an admin infrastructure staff member, I can duck that because I have admin rights. I can just copy the keys out of the main memory and use these keys to access all the data that is processed. If the data is encrypted on disk, so typically I use some encrypted disk from the operating system. I might use an encrypted object store, and there the keys are typically provided by the operating system, by the infrastructure staff. So that means despite being encrypted, the staff, the infrastructure staff, might have access to the keys. So that means I might not have enough protection of my data because the staff members that I need to protect against, they have actually access to the encryption keys. Now you can say, okay, I need a better key store. So most of the clouds, they have some key store. I can provide keys to my application via some API. And there is the problem that typically that key store is managed by somebody, say the infrastructure provider, and somebody controls access to the dashboard that gives access to the key store. And so there might be a problem that if I, as an infrastructure provider, manage that key store, how can I exclude myself that I cannot grant myself access to the keys that I used in the application? So we have some problem, kind of, I call that typically a bootstrap problem. So I need some keys to get access to the keys. I need some credentials, and somebody has to grant these credentials. And there I need to somehow find a solution so that I can get keys without knowing any keys or without trusting somebody that I shouldn't trust to give me the credentials to access the keys. So it seems to be a difficult problem. And to make that a little bit more difficult, we have actually a certain threat model in this context. So we might, first, the positive part, we might trust certain features of the CPU. So typically what we do is we check that the CPU is a genuine hardware CPU, is up to the newest firmware, it has the newest hardware features, and only if that is all satisfied, we might establish trust in a CPU. But what we don't trust is all the infrastructure provider. So the infrastructure provider has staff members, and we say that staff member might be in a different jurisdiction, might have different laws to follow. That means that this infrastructure provider might be required to give access to our data, to our code, to our secrets. And so therefore, we don't trust anything operated by the infrastructure provider unless we have sufficient protection against all these infrastructure teams. As an owner, I have also the problem that I might not know the whole code stack of the infrastructure provider. Might be open source, maybe then I can check, but the open source moves so fast that maybe I cannot check that really the version that is installed in the infrastructure in the cloud is actually an up-to-date without any modification. So can I really establish trust in all that infrastructure, even if it's open source? Because there are so many configuration parameters. So it's really difficult as an application owner to keep up with all the changes in configurations. So from that perspective, we don't trust, as an application owner, the infrastructure provider. We also don't trust necessarily the service provider that helps us to configure our application, maybe to operate our application. There might be also malicious participants in the service provider that might gain financial benefits by changing our code to get access to data. So, and what we need to make sure is that even the service provider that helps us to configure the application cannot get access to our data or keys. So we need to somehow separate, isolate them to make sure that our data is protected. If we are the application owner, we have to make sure that even service provider or staff member of the service provider cannot access our application code. So this seems to be difficult. And so how can we approach this? So we have been building some platform, the Scona platform, to allow you to build such applications where you protect yourself against the infrastructure staff, against the service provider staff. And the approach is as follows. So this is the kind of the currently supported features. There's some more in the pipeline, but this is kind of the state of the art. One idea is that we have some Kubernetes cluster. Let me start here on the bottom. We have set up Kubernetes clusters where we run our applications. And what is state of the art is that we make sure that we virtually air gap these Kubernetes cluster in the sense that we can only run application via manifests. So we send manifests, they are Kubernetes manifests, so YAML files, and we get back some YAML files that we can analyze, but we, as an application owner or service provider, we cannot execute in that cluster. So we cannot just go there via TLS and copy all the data. That should be prevented. So we want to isolate kind of our service provider staff and the infrastructure staff by air gapping our Kubernetes clusters. Second, what we need to do is we have to expect that some of our staff members are not trusted. They might have other motives to not work to support the application owner, but to support somebody else. So we have my insider adversaries. And from that perspective, we should make sure that no decisions can be done by a single person. It should always, the important decision should always be done by a group of persons. And we need to define if that is a really high impact decision that more people are involved. And if that's low impact, maybe only 2 people need to be involved. So we need some governance for our applications. Third, is that if governance is not sufficient, we at least should check later on and actually detect if something wrong was decided. So if there's a collusion of insiders, that we can at least detect this and see who caused a certain issue or data leak, for example. And let me go now through that approach. So I have a few more minutes. So I have some details how exactly that is done. First level is isolation. So we isolate the different services of our application. We make sure that the infrastructure provider cannot access our memory, our files. And we do that using confidential computing. But we have also on a higher level in isolation, where we make sure that we decouple ourselves from the Kubernetes cluster. So we don't want to let a service provider get access to the Kubernetes cluster, or if you want this feature. And so there you can just if you use Kubernetes, like Gardener-based Kubernetes cluster, you can use kubectl to send manifests, but you cannot do port forwarding. You cannot execute any programs. And that is one standard way of operating Kubernetes cluster in production environments. And we have on the Kubernetes side, we have just a vanilla Kubernetes, or it might be a Gardener vanilla Kubernetes cluster. And there we don't need any modifications of the Kubernetes cluster, just a modern Linux kernel, and also some CPU with trusted execution support. And then what we can do is we can just send manifests, we get back manifests, but no direct communication. And then when you do that, you can actually log all the interactions and you see who sent which manifests to that cluster. Okay, so that means we are kind of in a virtually air-gapped environment. If we set that correctly up, we cannot directly do a TLS connection. We cannot do any direct communication with our services. Now, there's the question, so how can we actually, I'm just, sorry. So how can we then actually establish trusted services in this context, in this Kubernetes cluster? So we do it in the following way. We can send manifests to that describe some custom resources, like a confidential service. And these custom resources are processed by a SCOAN operator. So this one operator that provides certain custom resource definitions. And one of them, custom resource definition, is a policy engine. So similar to in Zero Trust, you have always a policy engine where you define the policies, and then this policy engine enforces certain security properties. And so in the confidential computing, we have exactly the same. We have a policy engine, and that policy engine is actually also created in an air-gapped way. So you have the policy engine, in our case, is called CAS. So CAS stands for Configuration Attestation Service. So we describe that as a YAML manifest. We send that to via kubectl to the kube API. This is forwarded then to the SCOAN operator. The SCOAN operator, I forgot to mention, is also installed via Helm, via kubectl. So you can offline describe what you want to have, so declaration, then Kubernetes installs the SCOAN operator, and then with this new manifest, you can then create this SCOAN CAS. Now you have the question, how can I verify that my service that I start in that Kubernetes cluster can be trusted? Because the Kubernetes API might be modified. The SCOAN operator is also untrusted, so that might be modified. So how can I actually make sure that I can establish trust in a remote cluster and use that to enforce policies? So I have a policy engine that I use to establish trust in a remote cluster. So I have to first establish trust with that SCOAN CAS. So what we do is that we can attest the platform. So we get some report, a signed report from the CPUs that say, okay, in what state are the CPUs? We can verify that later on. We can also verify the kind of the initial state of that SCOAN CAS. We send that signed report to the SCOAN operator. The report also contains a public key that allows us, the public key to a random public-private key pair that the SCOAN CAS generated, and that allows us later on to establish a secure communication channel to the CAS. And so here in this case, we can generate attestation reports. These attestation reports can be verified remotely that this is one of our software that got started. And we learn a certain public key that is the encryption key for the policies, for our policy engine. And we can make sure that only that CAS can actually decrypt our policies. So we can actually push over some, we call them epols, so encrypted policies, via the standard kube API. It's managed by the SCOAN operator, all untrusted. Only the SCOAN CAS can decrypt them and actually make sure that it enforces these policies. So there we establish trust. Now we also have to make sure that these policies actually get into the CAS and are not somehow omitted by the kube API or the SCOAN operator. So what we can actually do is we have something that's called an audit log. Then this audit log we can is a cryptographic ledger. We can actually verify that the policies that we pushed over were actually created on that SCOAN CAS. so that this CAS enforces that policy. What I forgot to mention is that we also can, in this encrypted policy, we can generate keys, and we can also provide secrets that are predefined, so like decryption keys or encryption keys. We can create in the SCOAN CAS, so it's like a PKI as well, and a key vault together with some predefined secrets. And so if we have then established the policies, we can create start services. These services get attested by SCOAN CAS, and if they then verify, the verification of this attestation goes through, then they get key materials. And so in this way, we can solve the problems of bootstrapping trust into applications. So typically when I use a hardware security module, I need in my application credentials to talk to a hardware security module to get keys. Here in this case, it's kind of like Face ID. The application has a certain initial state. We make sure it runs in an encrypted memory region, and then if all that is satisfied, the SCOAN CAS gives it some keys similar to what they typically would use in a HSM, but we provide that transparently as environment variables, configuration files that are transparently mapped into the file system space of the application. So we make it as simple as possible to provide keys and configuration information to the applications. Okay, so I need to drink a little bit then. So this is kind of the first step. So we establish trust, we can run applications. Now I said we also need to make sure that we protect against insider attacks. And so what we have here in this context are governance. So all the policies can actually be protected against insiders that have policy access, that they can unilaterally modify these policies. So here's kind of a little diagram that shows what the problem is that we want to attack. We have a certain policy. We have some insider that wants to change the policy, say to leak all the data that is processed by the application by changing the policy such that application of the insider gets access and pushes them somewhere to some object store. And so we have had quite a few protection mechanisms, like we can create read-only policies. We make sure that only a certain policy with a certain hash value can get access to secrets, but that all is not good for a kind of a dynamic system, agile system, where we change policies all the time, where we change code all the time. We need a different mechanism to deal with insiders. And so therefore we rolled out governance. So we looked at governance for a few years and came up with a way of making sure that we can protect against insiders. And so the idea is that all policies are signed by governors, and we define how many governors need to change or sign off to policy changes. So typically we might have 3 governors that protect us or that govern a certain policy, and these governors can be reusable. So we define governors in one policy, and then a set of other policies can actually use the same set of governors. And the idea is that we define how many of these governors need to sign off a policy before a policy change can take effect. So in this case, maybe we have to have at least 2 signatures to make sure if we expect to have one bad insider in our governors, that we can have at least one good governor that needs to sign off too. So we could say 2 out of 3 governors need to sign. We can have actually arbitrary voting rules. I will show that in a sec. But it can, of course, also happen that all our governors would be bad apples, bad governors, and they might sign off, they might collude and might take wrong decisions. So we have to also make sure that if that happens, that we at least have a track of that thing happening, and that we later on can take actions of that. So these governors must not be able to change then the history, we have to have a history where we can show proof that these governors took certain decisions. So therefore, we have something that is called audit logs in the system. And so, but before I get there, quick examples. So how does this governance look like? It's like always, we have YAML files. So like Kubernetes, everything is, our policies are YAML based. And you can say, okay, to update a certain policy, you need the following conditions to be true. You require 2 votes or 2 signatures from these voter 1, 2, or 3, and require all signature of these veto members 1 and 2. So in here, this case, we would need 2 signatures plus 2 out of the 3. And so here, then you would have to have collusion of a certain number of governors for them to sign off in a bad policy, assuming that good governors would check the policy and make sure that only valid changes are signed off. You could also have policies where you say the application owner can sign off everything. So say the governors, they don't do their job, they don't want to sign anything anymore. Maybe you give priority to application owner can override everything. And so we have a general policy engine that allows you to enforce all these governing or voting rules that you might come up with for your application. Okay, so this is kind of governance. I mentioned already, so last topic here is audit log. So we can make sure that all the decisions that are taken are in cryptographic ledger. It's not a blockchain, but it's more like Google's trillion ledger, where we have a cryptographic chaining of records. And what we do is for all the policies that there are is we sign them, we put them kind of the hash value of this policy in our cryptographic ledger, similar to what Git does. So we have a history, but the main difference in our ledger is that you cannot change the history. So it's only moving forward. So you start with one policy for a certain policy name, and then you can change them, but you cannot never modify that history. So therefore, if there is some decision to change the policy such that I, as a governor, give myself access and I collude with the other governors, we can see that in the audit log. And so as I mentioned, the audit log is kind of a append-only cryptographically protected ledger that we can use to see what policy changes were performed. And we can do that offline to see if certain policy change should have not been performed. As a quick summary, what we do here is we support governance and audit. So kind of the idea is of governance is that I protect the future. So I want to make sure that changes in the systems are signed off by a sufficient number of governors. I protect my past. I can verify, have there been any policies in the past that shouldn't have been there? So therefore we have this audit log or ledger. And we have confidential computing in isolation to make sure that right now all the different secrets, data, and code is protected by having everything always encrypted. And the main engine that we use here is our policy engine. So the Scone cast that runs in a certain cluster, we can create that in a air-gapped environment. We can attest that air-gapped, we just manifest that we exchange. And so in this way, we can isolate our production cluster from the service teams. We can everything verify remotely without having the risk of leaking data by checking actually the policy or installing policies. Okay, that was it. I'm done. If you have any questions, happy to take some.
Thank you very much. I think I'm going to have a nightmare today with the conspiracy of 3 evil governors.
Okay,
So are there any
sorry about
questions? No problem. At least there's a proposed solution. Yeah, there's a question from Michael Mund. at least. Yeah.
A nice presentation. Thank you very much. I've enjoyed. My question, so as far as I understand, you are encrypting the enclaves of the processing unit, so nobody else will be able to put his hand on the information when it is processed.
Yes, correct.
In the past, there have been limitations. So let's say the processing units were not able to enlarge the space and the power, the resources for computation. So is this overcome, or are there still limitations we have to consider?
So the encrypted memory can be, or we have machines more than 500 gigabytes of encrypted memory. And if that is not enough, you can actually push some of the encrypted memory down in main memory, encrypt slightly differently. So in summary, we run Java application, Go application, Mono applications, so they're C#. So there is not anymore that limitation that used to be a few years ago.
Thank you.
So it's can run arbitrary large applications.
Thank you very much. And just another question: sometimes the processing units they cache. So the idea is to get faster. And this caching sometimes, if it comes hand in hand with secret information, it makes problems. There's a lot of trouble because you may not access the secret information itself, but you may have, unfortunately, access to the cache. So are you switching this kind of technology off? Or so what's your strategy behind that?
So caching, so there are different levels of cache. So the CPU cache is on, so most of the processing is done in the CPU cache. So the more you can cache, the more locality you have, the better is your performance. And the cache is flushed out when there's a context switch to a different application. So there you have to make sure that you have cache consistency and also that you don't have side channel attacks. They flush out the memory on this level. For caching in the file system, we actually have protection, so we automatically can encrypt your files. So I mentioned in one of the motivations that, see, if you use encrypted object store, somebody might have the key. So we automatically encrypt and data that we write out, we decrypt it when we read it in. And at that point, we also check the cache data. So we keep track of the latest modification of all the files. So if there would be old cache data, we can actually detect that is, we call it a rollback attack. So if you switch that technology on, we can actually detect that this is old data, and we would then say there's an IO error or what the application. You decide in the policy.
Thank you very much.
You're welcome. I guess
there's another question. Yeah. Or go on. We can do it however you want. Thor, you're the next one.
Yeah, hi everybody. So I'm at the Bahnhof in Berlin, so sorry if there's a little noisy here. But my question goes back to, I understood you to say that, okay, we must trust the hardware or the CPU. And we always are challenged a little bit with Intel SGX and TDX. And well, are these CPUs genuinely trustable, or in these secure enclaves, is it genuinely trustable in this context? What's your take on sort of the future here?
Yeah, so it's a good question. So I think all technology that we have is broken. It's just too complex. And what we need to have is a way of making sure that we have the up-to-date software, that we are aware of all security advisories. And the good thing is that we do the attestation. So we are forced to check that we have the up-to-date software for our services, and we have the up-to-date firmware for our CPUs and the up-to-date hardware. So every time an application comes up, we check, is that CPU, has it some hardware features that cannot be fixed by firmware? Is the firmware up to date? So there are a vector of security versions that are, every time your application starts in this context, are checked. And if the CPU is out of date, you have to opt in to make sure to say this is okay. So really, my assumption is we will continue to have security vulnerability. That is the same in Linux, that is the same in each piece of software that has a reasonable size. We have to expect there are vulnerabilities. And what we need to have is a way of dealing with the vulnerabilities. We need to check them. We need to make sure that we have no known vulnerability in the system. And then we have defense in depth, in the sense that we have this air-gapped environment, we test everything, we make sure that whenever there is a single point in failure, or a single point of vulnerability, that this alone cannot be used. And so from that perspective, we deal with that. And the most important part here that I should point out is that most of these attacks take lots of skills. So that means for most of the adversary that we face, that are system admins that might be need to copy our data, we protect against these, I think, with a very, very high probability. Against national attackers, we might have a little bigger, we need more defense, let's put it this way. Depends always who we are up against, but it's definitely good enough for most of the attacks that you need to consider in this context.
Okay. Any further questions? You can also post them in the chats if you want to. Okay, it doesn't seem to be the case. Oh yeah, one question in the chat. What do you think of an infrastructure integrated hardening solution, for example, Unigrid?
It depends how that integration should work. So hardening, whatever we do in hardening, we have support where we actually measure infrastructure, and where we kind of make sure that the infrastructure has additional protection. But whatever is from the infrastructure, my principal point of view is I don't trust, because I want to outsource this. Whatever is in the infrastructure hardening, it helps me to make sure that I have less attacks going to my application, but it's never good enough from my perspective, because I have the perspective of the application owner. Whoever protects the infrastructure, whoever hardens the infrastructure, is not anybody that I might trust or might not be able to trust, because I have requirements that I should not trust that. Like in the e-health domain, I want to outsource application into an infrastructure and that infrastructure is hardened and it's well maintained, but it's operated by somebody that I don't trust. So therefore, I say it's good to harden, but I say it's not good enough for me. There was some more.
Yeah, there are two more questions again. I think Tor was again first, and then Michael again.
Yeah, hi again from Bahnhof. These mechanisms, when they are fully implemented and running, what kind of overhead are we talking about? I imagine this, you're talking the e-health domain, that we're talking about, some sort of medical connect devices that are distributed at some sort of medical facilities, and data gets processed. What kind, do you have data on the overhead that it takes to guarantee this level of data, management of data security, man?
Yeah, so we have measurements, we have lots of measurements, and there is some dependencies on the application that you're running, so how much locality it has. There's also dependency on which operating system kernel you run. So if you run an older kernel, you have slightly higher overhead than if you have a new 6.2 kernel from Linux, because you have more features enabled that give you performance. So from the performance perspective, so from the good part, if you want me to give you some good examples, if you run Python, there is no difference between a Python application running natively or encrypted. If you run a high performance computing application that is highly tuned for native execution, there you might see 20% overhead in some cases. So we have seen logged into MariaDB. So there, when we don't do extra tuning, we had some 20% overhead by running it encrypted. And I think that is fine as long as you can scale, because you run in a Kubernetes cluster, you just have a little bit more than infrastructure that you need to make up for that, or you need to have better performance. So if you go from Python to Rust, you get a 100-fold speed up, and 20% later on you add for confidential computing. So from that perspective, I think the overhead is typically in the noise. So people, I think they don't worry too much about 20%. Okay, there was one more question.
Yes, Michael, but you put your hand down again. I don't know.
Yeah, I was just looking at the websites and I thought I had a question, but reading a little bit further on, I think it is answered. So I'm sorry. So I'm fine.
Okay. So just for your information, Rene, who asked the question on the infrastructure integrated hardening, also replied in the chat to your answer, Christof, and he said, okay, it makes sense. So the type of infrastructure here, which is decentralized with shared data storage and access, may be taking away at least part and perhaps even all of your concerns. Just for the record. And then
okay. So there again, how can I establish trust in my infrastructure? So if that is confidential, I can attest it and I know the software, maybe I can use confidential infrastructure services. But if I have, say, a Ceph service, we talk about shared storage, how can I trust that the encryption mechanism by the, let's say, my Ceph cluster is really protected? So how can I make sure that there is no, how do I prove that my infrastructure actually does not leak my keys? So typically I need to have a security argument, and the less components my security argument has, the easier it is. And here, everything that I get from the infrastructure gives me practically more security, that's for sure, but it doesn't help me to exclude certain actors like people in the infrastructure that have access to my sharded and data, encrypted data, would be my thing. We can take that. Happy to discuss that a little more if you want. Okay. Okay, I got a link here.
yeah,
Okay. Good.
maybe yeah, a discussion to be continued after the tech talk, after you read the paper. Okay, great. So I think, yeah, in the sake of time, we should move on. I would just like to have some final minutes for yeah, for the news and so on. So thank you very much, Christof, for your presentation. It was great, very interesting for everyone, I think. And now if you would just allow me to share my screen for a couple of minutes, then I can go through my last slides as usual. So the first thing, as usual, if any of you has an idea for a Tech Talk presentation, then just please let us know, and we are happy to plan your presentation. We have some ideas for the next months in the pipeline, but just let us know if you have anything else. And yeah, we're always happy to hear about new topics or things that you might be interesting and you want to share with the rest of the group. So that's the first thing. The second thing is the news and events that I was mentioning. So again, I usually present here some news or some events or some information that we have from the association, but it's open to everyone. So if you have any other events or any other interesting things that are going on that you would like to let us know about, then just yeah, let us know right now. So you can just unmute yourself and let us know. Otherwise, I wanted to mention that from September on, we're moving the time of the ALASCA Tech-Talks to Fridays in the morning at 11 a.m. This is due to the current issue that we have, that the Tech-Talks are happening at the same time as the YAUC meetings. So YAUC being the first open source project of the association, it doesn't make sense to have the meetings at the same time. This was some historical reasons, so now we're moving it to Fridays at 11 a.m. So all of those, everyone who's in our mailing list for the Tech-Talks will receive the new calendar invitations for Fridays. Otherwise, just bear that in mind. And if you want to join the mailing list, then just send us an email. And then also some news that we have, that ALASCA is growing. So there are a couple of new members in the association, and I won't say too much today, but just stay tuned to our social media on the website, because we will be communicating that in the next days or weeks. So now an opportunity for anyone else to add anything, any news or any events that you think would be interesting. Okay, so as I mentioned, you can subscribe to the mailing list if you want to receive the information every month of the next Tech Talk. We always send calendar invitations. Otherwise, you can access all the information on the ALASCA website. So we have now a dedicated ALASCA Tech-Talk website within the ALASCA website. So just check that out there. And a reminder that we always we record these videos and then upload them on YouTube. So if you miss one Tech-Talk, then you can always watch it on YouTube afterwards. And so with this, the last thing I have to say is that save the date for the next Tech-Talk, which will be, as I said, this time Friday, 11 a.m. on September 29th. We have a presentation by Christian Behrend from 23 Technologies, perhaps with some other colleagues. And they will be presenting why they decided to move 23KE to an open source project, and some of the challenges, technical and organizational, that are related to that. So that's what's coming up in September. And yeah, I would be very happy to see all of you again in 4 weeks, more or less. So yeah. With this, I think we're finished. I would just like to thank all of you for being here, for your participation, and particularly Christof for sharing with us this interesting topic. And with this, yeah, just hope to see you soon again, and enjoy the time until the next Tech Talk.